Hello, back to Engineering 201, Electrical Fundamentals. And I wanted to pick up where we left off last time, working on transient problems using that six-step method, and tackle one more problem, probably our most challenging problem. You can see on this problem it's got a dependent source, so that's going to challenge us particularly in step number 5. So let's get started with this. We would like to, with this one, we'd like to find what V0 of T is. That's what we're looking for. And with step number 1, we're going to assume the form that V0 T is equal to K1 plus K2 e to the minus T over the time constant. And again, as always, our task will be to find the pieces so that we can get K1 and K2 and the time constant. Now the stipulation for this equation is as a constant forcing function. So this is a constant value. Presumably that would give a constant current here. So this Ix, 2000 Ix, that's also going to be constant. So these sources are constant. We only have one energy storage element, one capacitor. So I think we should be okay with this. Well, I think I'm going to pull up another slide now to look at 2, but we'll come back to this. Maybe we'll put our scorecard here, where we keep track of things. The capacitance is 100 microfarads. Then with step number 2, we're going to assume steady state and have to get the voltage across the capacitor at t equals 0 or 0 minus. So that's the next thing we'll go to. So let me flip the page here. And we get that, this being, this was step number 1. Then we have step number 2. Step number 2 is assume the switch has been open for a long time. Assume this has gone to steady state. We open a capacitor if it was an inductor, and we did last time one with an inductor. We'd short out the inductor and find the current, but since it's a capacitor, we open the capacitor and we find the voltage across the capacitor. We're looking at this. This would be time slightly before 0, because at 0 the switch closes. Well, if you look at this, if this is open and this is open, the problem is not quite as ugly as it looks. We really just have one loop. We're not going to have any current going down here. I would be equal to 0 there. And of course wouldn't have any current going through here. So I could really just take a loop through here. And I think that I will say that loop is Ix. And so we've got Ix there and we have a function of Ix there. So looking at the loop equation, what are we going to have then? If I start right here, I've got a gain of 12, so I'm going to say minus 12 plus Ix times 4k, then plus Ix, because there's no current in here, so it's still just Ix, times 6k. And then I get down here and I have to do what? I'm going from positive to negative, so that's a drop, so that'll be positive Ix times 2000, which I'll just say is 2k. That's not k ohms, but it would have some units to convert current to voltage because it's a current controlled voltage source. So I'll just go ahead and take that as 2000, 2k, keep the math easy. That gets me back to my starting point, doesn't it? I can say that's equal to 0 by Kirchhoff's voltage law. So I've got then 4k, 6k is 10k, 12k. Ix is equal to 12. That goes over to the other side. So Ix is equal to 12 divided by 12k, which gives me 1 milliamp. So now I can say that the voltage across the capacitor, because there's no current going through here, so there's no voltage drop across this resistor, the voltage across the capacitor at t equals 0 or 0 minus is really just going to be this voltage here, 2000 Ix plus the voltage across there, which is, if our current is going like that, Ix turns and goes like that, I could really just say it's Ix times 6k, right? So this turns out to be equal to Ix times, this is, remember, 2k. So 2k and 6k is 8k. So I've got 1 milliamp times 8K gives me 8 volts. Okay, gives me 8 volts. So that was fairly easy. Let me put that there, 8 volts. So now with step number 3, I'm going to throw the switches and actually then get to the business of looking for this, what I'm looking for. That is, I'm going to be looking for V0 T equals 0 or 0 plus if you want. So let me flip the page then. We'll notice that this 8 volts, that would be taken as positive there and negative there. That's going to be important when we put the source in. So let me move to the next page. So when I put the source in, I'll put it in positive, negative, and I have 8 volts. So we're looking at step number 3. Okay. And we close the switch, we throw the switch, we move the switch to its new position, so this is forever closed, and we replace that capacitor with the voltage source that we got from step number 2. So this, at this point, because we have a branch here and we have a branch there, there's going to be a current through here and a current through there. I think I'm going to go ahead and look at this in node analysis, and maybe I'll mix this up. Maybe I'll put a current here. I always like the current leaving the node. This is one great big node up there, isn't it? I could say that that is, maybe I'll call that Vx. And I'm going to call this I1, and maybe I'll call this then I2. Why don't I call this I3, and we'll call this I4. And you could, if you wanted to leave IX there, that'd be fine. I just like my currents leaving the node, so I'll take I1. So if I use Kirchhoff's current law, I can say that I have I1 plus I2 plus I3 plus I4 is equal to 0. And if you had IX, you just have a minus IX there instead of an I1. So if we go through this and we make our substitutions, if I1 is going this way, I have to find the voltage that way, which is going to be minus 12 plus Vx. So minus 12 plus Vx divided by 4K, plus I2, which is simply Vx over 6K, plus I3. Oh, I3 is going to be a little tricky. I got to find the voltage across that thing, don't I? Which means I have to go from here down to here, which is going to be minus 2K Ix, and then I have to add to it Vx, and divide this whole thing by what, 6K? So minus 2K Ix plus Vx, and I divide all by 6K. Yes, good. We might have to make a substitution for that in a moment. Plus I4. Well, I4 I have to go like that, don't I? So I'm going to drop 8 minus 8 plus Vx divided by 4K. And like I said, these problems are good because they really reinforce. We've already done a mesh analysis problem. Now we're doing a node analysis problem. It's actually got some kind of tricky pieces in it, so it reinforces the things that we have learned all term long. Well, let me go through this then. I could say that I have minus 12 plus Vx over 4K plus Vx over 6K, and then I'm going to have what, a 2K over 6K, which gives me, I'm going to say 2K over 6K is a third, and then I have to, and I'm going to break this up, so I'm going to add to this plus Vx over 6K. So in here now I have a minus Ix, right? Isn't the minus Ix going to go in there, the negative sign? Well, what's minus Ix? Well, minus Ix is really I1, isn't it? So minus Ix is equal to I1, so I could say that this was Vx minus 12 divided by 4K. because minus Ix is I1. So I have this Vx over 6, and then I have plus a Vx minus 8 over 4k is equal to 0. So I think I'll multiply everything by 12k. When I multiply everything by 12k, that I get minus, 36, because 4 goes into 12k 3 times, plus 3 Vx plus 2 Vx plus, and then this is going to be, what did I have here? Same thing as this, right? But then I divide it by 3, so I'm going to have Vx minus 12. So I'm taking this same piece right here, dividing it by 3 because of that third. And then I'm going to have plus 2 Vx plus 3 Vx minus 24 is equal to 0. So if I continue on up here, how many Vx's do I have? I have 3, and 2 is 5, and 1 is 6. 2 more is 8, 11. 11 Vx is equal to, when I move these over to the other side, I have positive 36. Positive 12 is 48. Is that right? And positive 72. Okay, let me double check that so I don't propagate an error. Yeah, I think we're good with that. So I could say that Vx is equal to, what, 72 over 11 volts. So what? Well, what are we looking for? We're looking for V naught. So I could say then that V naught at t equals 0 or 0 plus is going to be equal to this total Vx, but then I have to subtract off, because I'm just looking for the voltage there, so I'm going to have to subtract off that 2000 Ix, right? So minus 2000 Ix plus Vx again. So I have 72 over 11 minus 2k times Ix. Do I have Ix? Well, Ix is just the opposite of this thing, isn't it? So I would say that I have 2k times 12 minus Vx over 4k. Because I1 is the opposite of Ix, so I put a negative sign in here. The 12 becomes positive, Vx becomes negative, and then Vx is 11 over 72, so I have Vx is 72 over 11, excuse me, 72 over 11, then minus 2k over 4k's, the k's cancel, and I have a half, 12 minus Vx, again, 72 over 11. So I'll get a number for that. Okay. I seem to, maybe I made a mistake with my calculator here. Let me double check this. Yeah, there we go. I think I just made a mistake on my calculator. I wasn't getting what I'd got in my notes earlier. So this is a positive 3.82, 3.818, so 3.82 volts. Positive 3.82 volts. Good. Okay, so we got that. So I can come back here to my scorecard. We've got this is 3.82 volts. So the next thing we're going to look for is V naught at t equals infinity, right? So I will move on then. We've got this one. So we've got step number 4. Step number 4, what do? Well, time goes to infinity. We're looking for this voltage at t equals infinity. Capacitor looks like an open circuit to at infinity, so we open that up. So what are we going to have? Well, we're going to have something that is very similar to what we did before. I mean, if we go back and we look at this, virtually the same here, except I4 goes to 0. Exactly the same. So let me take a look at that. We could say same as step number 3 with I4, this current there, I4 being equal to 0. So I can go back and I can reproduce that. I'm going to have I1 plus I2. So I've got I1, I2, I had I3, and this was the I4, which is now equal to 0, right? Okay, I1 plus I2 plus I3. I1 plus I2 plus I3 is equal to 0. I'm going to take my reference ground there. We'll take this as Vx. So I look at my substitution. I had minus 12 plus Vx over 4k plus Vx over 6k plus, what do I have? I'm just going to say that this is a third, and then Vx minus 12 over 4k. Make that substitution that we did a little bit earlier there. Okay. Plus, what is I3? Whoop, I've still got another term for I3, don't I? I have that because this was back here. That's your I3, and this whole thing ended up being I3, didn't it? So I'll have a third Vx minus 12 over 4k plus Vx over 6k, just saving a little bit of work, plus 0. That was your I4, wasn't it? Is equal to 0. Okay, so I've got something like that. I think I'll multiply this again by 12k. So I'm going to have minus 36 plus 3Vx plus 2Vx plus Vx minus 12 plus 2Vx is equal to 0. I don't have those last two terms because I4 is equal to 0. So what do I have here? 3, 5, 6, 8. 8Vx is equal to, this goes over minus 36 minus 48, so I have 48. So Vx is equal to 48 over 8, which is equal to 6 volts. Now, what are we going to do with that? Well, again, we say that we're looking for this thing, right? So I've got then that, just like we did before, that V naught at t equals infinity is going to be equal to, I have to to get the voltage across here, which is voltage across there, I've got to subtract that. So I've got to say minus 2000 or 2K Ix. That gets me down here. So minus 2000. There's that. Minus 2000 Ix plus Vx, which is going to be equal to, what do we get Ix as? Ix is minus I1, isn't it? So I could say that I have 2K times minus 12 plus Vx over 4K. You see, I didn't change the sign on that, Ix being equal to minus I1 again, but because I had the negative there, I got rid of that, and then I just wrote that I1 in there. I think I'm okay. Plus Vx. So I have a half times Vx minus 12 plus Vx. So I have a half times Vx, and we say that was 6 minus 12 plus 6, which gives me, what, 6 minus 12 gives me minus 6, so minus 3, so I come up with 3 volts, don't I? So 3 volts. So I come back to my scorecard here. V at time equals infinity is 3 volts. 3 volts. Okay. So that was step number 4. So then on to step number 5. I mean, keeping up on the scorecard, what are we looking for? Well, on the scorecard, step number 5 is to find R Thevenin, because with R Thevenin, we can get the time constant, right? That's step number 5, R Thevenin. That's where we're going to have to start earning our money on this problem, because we have that dependent source. So let's do that. Too many papers here. So step number 5, which is to find R Thevenin. Okay, find R Thevenin. So I look into this energy storage element. The switch is still closed. I take out the energy storage element, and I look in there, and I ask what is R Thevenin. Okay, and we know we can't use the shortcut. All the problems up till now, they did not have this diamond. They did not have a dependent source, so we could use the shortcut. Let's emphasize this. No shortcut. So we're going to have to go through this and rather find V open circuit and I short circuit, and then with that we know that R Thevenin is equal to V open circuit divided by I short circuit, right? Okay, so that's our task. Well, I think I've seen this circuit before. If we look at, did we see something like this back in step number 4? Yeah, this was almost the same, wasn't it? So let's look at this. And there'd be nothing wrong with just grinding through this and finding V open circuit, but this circuit that we have here is really the same as this circuit here. So we could say for V open circuit, that would be the same as Vx in step number 4. Now that's not always the case, but in this particular problem we had this Vx up here. When this is open, your current through here, I is equal to 0, right? So the voltage across here is equal to 0. And then, so the voltage across here becomes the same as Vx, which is that voltage across there, right? So we can say then that V open circuit is equal to the Vx that we found here, 6 volts. Okay, and if you wanted to go through analysis and find the open circuit voltage across here, you could, and you'd come up with this. I'm just trying to save a little time and effort. If you don't see that, that's fine. You just go through here and find that, and you'll oddly enough, do exactly the same analysis as you did in step 4. Now, this isn't always the case. Don't think that, well, you just go back to step 4 and get that. No, it just happened to be where the capacitor was and where the switch was. It worked out nicely for us. Well, V open circuit is 6 volts. I still got to find I short circuit, don't I? So if I put this short across here, and I start looking for I short circuit, so I talk about I short circuit there, I could do this problem again. I'll take I1 and I2 and I3. So solving for I short circuit, we would have I1 plus I2 plus I3 plus I short circuit, right, or I4, whatever you want to call it. Now that this is shorted out, it's not equal to 0. When we were talking about V open circuit, I said this was equal to 0, but now it's non-zero. I short circuit is equal to 0. So what are we going to have? Oh, we're going to see similar terms to what we've seen before. Minus 12 plus Vx over 4k plus I2, which is Vx over 6k, plus that third times Vx minus 12 over 4k. Make sure I got that right. Yeah. So these terms have been the same as ones we've been working in the past. Plus I short circuit. I mean, these are all the same that we've done in the past. I short circuit's the only one that's different. What's that? That's Vx over 4k, isn't it? Well, I guess I have to add to this one, don't I? Going back here. And remember this one, I3 was that, which we expanded out, so I've got a plus Vx over 6k. I'm just avoiding going through this step and having to make the substitution for Ix, so I come down here and use this one. That is I3. So now I have what? I short circuit. So this whole thing again is I3. And what's I short circuit? I short circuit is right there. It's going to be Vx over 4k equal to 0. So I can take that thing, I can multiply it by what? 12k. When I multiply it by 12k, I'll kind of cheat here. So multiply by 12k. And we're going to have minus 36 plus 3Vx plus 2Vx plus Vx minus 12 plus 2Vx plus, what's that, 3Vx is equal to 0. So Vx is 3, 5, 6, 8, 11. 11 Vx is equal to 36 on the other side, 48. Is that right? Yeah. So Vx is equal to 48 divided by 11. And we know here, because I short circuit is equal to Vx divided by 4k. So we put that in there. 48 over 11 divided by 4k, which gives me what, 12 over 11. Yeah, 1.091 milliamps. That's I short circuit, isn't it? So I could say then that R Thevenin, let's carve out a little space here. R Thevenin is equal to V open circuit divided by I short circuit. Do we get V open circuit? Yeah, that was 6 divided by 1.091 milliamps. We get 5.5 k ohms, don't we? 5.5 k ohms. 5.5 k ohms. So let me update my scorecard here if I can find it. R Thevenin is equal to 5.5 k ohms. So again, step number 5 is where we really don't like to see these things. We can't use the shortcut then, but when you can't use a shortcut, you just do your V open circuit, you do your I short circuit, find that ratio, and it's not a big deal. Not a big deal. We're off and running with that. Again, at this point, probably more tedium than difficult, more tedious than difficult, and as far as homework problems go and whatnot, it's good practice as we continue on. Well, let's start to put this all together. We know then that the time constant is going to be equal to R Thevenin times the capacitance. Okay. So R Thevenin times the capacitance. So we've got then R Thevenin 5.5 times 10 to the 3. I have to be real careful when you use the base units. 5.5 k ohms. And then what was the capacitance? Microfarads. 100 times 10 to the minus 6. So that turns out to be equal to, what, 0.55? Is that right? Seconds. Let me double check that. Yep. Okay, so we're good with that. So I think now we're set to go to step number 6 and put this whole thing together. So let me finish up on a fresh page here. Page number 6, step number 6. And I'll use my scorecard here, a cheat sheet, to put this all together. We know that the solution, going back clear back to step number 1, is that V0 of t is equal to k1 plus k2 e to the minus t over the time constant. So k1 is going to be equal to this, isn't it? Okay, is equal to 3 volts. And k2 is going to be equal to the difference between these, 3.82 minus 3. Is that right? Yep, 3.82 minus 3, which I get 0.82 volts. So when I put this together, I've got then that V0 as a function of time is equal to K1, which is 3, plus 0.82 e to the minus t over the time constant, 0.55, and this is going to be volts. Okay, so 3 plus 0.82 e to the minus t over 0.55 volts. So that's pretty good. One thing I forgot to mention as we were working on R Thevenin, it was nice to know that these are both positive. If one's positive and one's negative, you can't have a negative resistance, so that's good news there. And I think we can have some confidence in our answers here and be happy with this. So it's a fairly challenging problem, not in terms of its difficulty, but in its length and tedium and whatnot. But again, like I've said many times, good for review at this time in the term as you start to study for the final and things like that. So when we get together next time, we'll start our last section of this term, which will be introduction to AC analysis, some basic AC concepts, some basic AC analysis, and start the introduction for those people that are going to continue on with this next term when we spend a lot of time doing AC. So should be a fun subject, an interesting subject, and take care till then. Thank you for watching.